An EC fan costs more to buy than the AC fan it replaces. Whether it costs less to own is a calculation, not a slogan, and it is a calculation you can do yourself in 5 minutes with numbers you already have. This video gives you the method, shows where the savings physically come from, and is honest about the cases where the AC fan wins. First, where the saving is not. At full speed, flat out, an EC motor is somewhat more efficient than a comparable AC induction motor, but the gap at full load is modest. If your fan genuinely runs at 100% duty around the clock, the energy argument for EC is thinner than the brochures imply, and you should run the numbers with particular care. The real saving lies at part load, and it has two ingredients. The first you have seen in this series, the cube law. Slow any fan to 80% speed and the air power falls to about half. That ingredient is free with any speed control, EC, or AC with a drive. The second ingredient is EC specific, how efficiently the machine turns electricity into shaft power while running slow. This is where induction motors suffer. An induction motor plus external drive at low speed and low load drifts away from its best efficiency, and the drive adds its own losses on top. The EC package, magnets instead of induced rotor current, electronics matched to the motor they live inside, holds its efficiency over a much wider speed range. Same cube law for both, the EC keeps more of it. So the honest comparison is never EC versus AC at nameplate. It is the total electricity through a year of your actual duty profile, how many hours at full speed, how many at 60%, how many at 30%. The more of your year is spent slow, the wider the EC advantage grows, and a fan on a schedule or a sensor spends most of its life slow. Let us put arithmetic on a worked example, and these numbers are illustrative, chosen to show the method, not a quotation. Suppose the AC option draws 1 kWh duty and runs 5,000 hours a year, 5,000 kilowatt hours. At 20 cents per kilowatt hour, $1,000 a year. Now suppose the EC option, over your real mix of speeds, averages 30% less electricity. $300 a year saved. Payback is then one division. If the EC fan costs $600 more to buy, 600 divided by 300 is 2 years. After that, the saving is yours for the remaining life of the fan, often a decade or more. Change any input, your tariff, your hours, your price difference, and the division updates instantly. That division is the entire financial case, and now you own it. 3 inputs dominate that division, so check them in order. Electricity price, doubling the tariff halves the payback. Running hours, a fan running 1,000 hours a year pays back 5 times slower than one running 5,000. And the part load fraction, a fan that never slows down barely benefits. Hours running slow times expensive electricity is the EC sweet spot. Where does AC still win? Short running hours, a fan used occasionally may never repay any premium. Genuinely constant full load, where the efficiency gap is smallest. Very cheap electricity. Harsh environments beyond the electronics temperature rating, where a plain induction motor simply survives better. And cases where a failed EC module means replacing a motor, while the equivalent AC repair is a cheap external part. None of these are exotic, they are worth checking honestly. There is also a control dividend that the payback division does not capture. An EC fan takes a 0 to 10 volt or PWM signal directly, no external drive, no drive cabinet, no extra wiring losses, and it can hold a set point, ramp gently, and report faults. If your alternative was AC plus a variable speed drive, price that drive, its enclosure and its installation into the comparison, because the EC fan swallowed all of it. A note on retrofits specifically. The attractive arithmetic above assumes the new fan actually runs slower much of the time. A retrofit that swaps the motor but keeps running flat out at a fixed speed collects only the modest full load gap. The saving comes from control plus efficiency together. Installing EC and never using the speed input wastes most of what you paid for. So the procedure is, write down your duty profile, hours at each speed. Estimate the electricity for each option across that profile. Multiply by your tariff, subtract, divide into the price difference. If you send us those inputs, the profile, the hours, the tariff, We will run the comparison against real fan data and send back the division with its assumptions visible, so you can challenge every line of it.